Wendy and I were asked to give a little presentation here on managing lead in drinking water distribution systems, and we've split it up. So I'm going to discuss some of the research outcomes that we've produced in our group at Dalhousie at the Center for Water Resources Studies over the past few years. And then I guess Wendy's going to maybe talk a little bit about how those have informed policy at the utility. So I'll get started. So of course, we care about lead in drinking water because of its health effects. As we all know, lead in drinking water is correlated with lead in blood, is often correlated with lead in blood. That's been shown in repeated work, recent studies and studies further back. Elevated blood lead is strongly linked with learning deficits and attention deficits in children. And that's the most important, or probably one of the most important health effects. It's certainly the one that occupies most of our thinking in terms of limiting drinking water lead exposure. Of course, at higher levels of lead exposure, there are some really nasty health effects, including even death. But we're mainly concerned with the low-level exposure and its effect on children, although for adults, there are impaired cardiovascular health related outcomes at low levels of exposure that are also a potential concern. So when they are present, lead service lines are the principal source of lead in drinking water. A recent study estimated that there were something like 5 to 7 million lead service line connections remaining in the United States, although I've seen recent estimates that were 3 times that, or close to 3 times that. So it's not really known how many lead service line connections there are in the United States. Quite a few left. Certainly they were installed widely throughout Canada, and there are a substantial number left in Canada. This is also an international problem. Whether lead service lines are present or not, leaded solder connecting copper pipes within premises plumbing and leaded brass can also represent important sources. So the diagram here just indicates the service line connecting the public water main with the premises plumbing of the home. The property line divides the service line into the public and private portions, which I'll refer to shortly. So the lead service line is most often associated with peak lead levels as determined by profile sampling. And by profile sampling, I mean opening a drinking water outlet and collecting a series of samples of equal volume to represent lead release to either a portion of the total volume contained within the entire plumbing network or the entire volume of water contained within that plumbing network from the outlet to the public water main. So this is an example of a 13-liter sample profile. I'll be referencing profiles of various volumes, but invariably the last liter represents a flushed sample, so that it is lead release to free-flowing as opposed to stagnant water, whereas the others all represent lead release to stagnant water, 1 through 12 in this case. So lead is represented by yellow bars here and copper by blue bars. This particular residential site was plumbed with copper, and so copper levels are highest in the first 2 to 3 liters, representing the premises plumbing at this particular site. Lead levels climbed from the first drop, liter 1, to liter 4, where they hit their maximum. So something like liters 4 to liter 9 represent the lead service line in this case. We can't be completely sure because we don't have precise plumbing configuration information for this site, but we do know there's a lead service line, and liters 4 to liter 9 are representative of peak lead levels and likely show the contribution of lead from the lead service line. So it's not surprising then that when we completely remove the lead service line, it has a substantial impact on lead levels. Not at all surprising. What's perhaps a little bit more interesting is that removing the lead service line substantially reduces lead release from the premises plumbing within the home. So I've shown a data set here for 56 sites within the Halifax system. I've represented the distribution of lead levels both before and 1 month after full lead service line replacement as sample quantiles. And the most important piece of information here is that the sample quantiles fall below the y = x line indicating that pre-replacement lead levels are substantially higher than their post-replacement counterparts. I've actually quantified here the percent of the pre-replacement lead level remaining and estimated it using the dashed lines. The corresponding ratios indicate the percent or the fraction of the pre-replacement lead level remaining at the 1 month follow-up. So at that 1 month follow-up, we have 13 to 65% of pre-replacement lead levels remaining over a 5-liter sample profile. So a substantial improvement here, quite rapidly. Partial lead service line replacement is a bit more complicated, or quite a bit more complicated. The partial lead service line replacement typically refers to replacement of the public section of the lead service line with copper, as most of us will know. Partial lead service line replacement in Halifax was associated with increased lead release from standing samples at the 3-day follow-up and at the 1 month follow-up, where we collected data. So this plot shows box and whisker plots of the increase in lead release relative to beforehand at that 3-day follow-up round and at the 1 month follow-up round. So for standing samples, that is liters 1 to 4 in this case, there are substantial increases relative to pre-replacement in lead levels. So something like 50 to 75% of sites sampled had increases in those standing samples. Some increases, although rare, we did see extreme increases relative to pre-replacement, going up to and including over 10,000 micrograms per liter. Increases on the whole were lower, but still worth noting and still quite significant. So, thinking more long-term, at 6 month follow-up after partial lead service line replacement, 27% of first draw lead levels were greater than 15 micrograms per liter, compared with just 13% pre-replacement. 15 micrograms per liter is, of course, the action level for the US EPA lead and copper rule for lead. It's also a health-based threshold, so the Centers for Disease Control and Prevention recommend that children and pregnant women not consume drinking water that has more than 15 parts per billion lead. So I've represented this graphically, showing all of the observations that we collected where a water sample had greater than 15 micrograms per liter lead. The top row is pre-replacement, and the bottom row is 6 months after partial lead service line replacement. And it confirms visually what we saw with the frequency calculation, which is that the occurrence of elevated lead levels is not diminished following partial lead service line replacement, even in the relatively long term, 6 months after that replacement event. So the main result of our sampling pre and post lead service line replacement was the conclusion that, based on the Halifax data, partial lead service line replacement was not a reliable strategy for reducing lead at the point of use. We also gained some insights into the role of iron-lead interactions in drinking water systems and the role that they play in encouraging elevated lead release. So online cast iron distribution mains, as we all know, are common in many water systems, including the Halifax system. We showed through these data that an unlined iron main was actually linked with elevated lead release from lead service lines downstream. And this was in agreement with previous but recent published work linking iron and lead concentrations in drinking water. So of course, iron in drinking water is probably most often thought of as an aesthetic concern, but the iron oxide particles that make up red water can serve as a carrier phase for contaminants, including lead. So we, through the data that we were collecting through the Halifax water lead service line replacement study, we developed and applied a chromatography method to analyze and characterize small colloidal or nanoparticulate iron and lead in drinking water. We applied this at 23 residential sites with full lead service lines, partial lead service lines, or recent full replacements. And our main conclusion was that colloidal lead and iron were present universally whenever there was a source of iron. And also that they were strongly correlated under various separation conditions. So these chromatograms show retention volume, intensity of iron and lead as a function of retention volume. So here retention volume is an indicator of particle size. So small retention volumes are associated with large particles, and large retention volumes associated with small particles. So this is in effect an element-specific relative size distribution. And what we found was that no matter where we looked, we saw a strong correspondence in the relative size distribution between the two elements, iron and lead. And also under various separation conditions, we invariably saw the same thing. So using chromatography methods, we determined the colloidal lead were present and appeared to be related. We also determined through size fractionation that the colloidal fraction represented a significant and even a majority of lead and iron, total lead and iron. So I've shown here a coarse size fractionation scheme. We performed this for lead, but we also performed it with iron. I'm not showing iron, only the lead. So in this case, we've fractionated total lead by size into 3 fractions, greater than 450 nanometers, between 50 and 450, that's the orange bar in the middle, and then finally less than 50 nanometers. I should point out that the smallest size fraction did include colloidal lead and iron as detected by chromatography methods, so it shouldn't necessarily be considered truly dissolved or truly soluble either. So a significant fraction of the total concentrations of these metals was present as a small colloidal or nanoparticulate fraction. This has a few implications. I think one of the most important is that if these colloidal particles did originate from corroded iron distribution mains, they could have a major impact on both lead solubility and lead mobility, which is something I won't go into further here, but it's something we're actively investigating. So not only did we determine that in the colloidal or nanoparticulate range, lead and iron were present and appeared to be interacting, we also used data from the lead service line replacement study to show that lead concentrations were higher in the presence of an iron distribution main, especially a disturbed iron distribution main. So these bar plots, this bar plot, groups lead concentration according to lead service line replacement type, either a partial replacement or a full replacement, and iron main condition. So we had pigged iron mains, which had scale mechanically removed, potentially releasing a tremendous amount of iron to water. We had iron mains that were pigged and then subsequently lined with an inert liner, which is probably a substantial improvement over just pigging. We had mains that were not disturbed, and then finally we had ductile mains that were installed with an inert liner. So a substantially higher lead release when the upstream service line was cast iron, and moreover when it was a disturbed cast iron main. So we replicated these observational results experimentally using a model distribution system. This system comprised online cast iron distribution main sections and PVC, inert PVC distribution main sections, and recovered lead service lines from the Halifax water system. And the main result of this study was that the presence of an upstream iron main was associated with elevated lead release from those lead service lines. Moreover, that release was not diminished, the difference between release from iron and PVC distribution mains was not diminished by increasing the concentration of an orthophosphate-based corrosion inhibitor from 0.5 to 1 milligram per liter. So this plot just shows that main result. Graphically, we have total lead over experimental time, color-coded according to the upstream distribution main material. And each point represents an average of 4 lead service lines, or lead release from 4 lead service lines, with the overall trend shown in red. So a clear stratification of lead release according to distribution main material, despite the increase in orthophosphate. So we've devoted a substantial portion of our time lately to analyzing and understanding the mechanisms at play within a lead service line when iron particles are present. And those interactions appear to be fairly complex, involving both absorption and electrochemical phenomena, as in galvanic interactions. I won't go into those in any more detail here, but I'd be happy to answer any questions concerning that. I guess for the last portion of this presentation, I want to focus on some new data related to orthophosphate lead release inhibition by orthophosphate in the Halifax and Dartmouth water systems. So in April 2016, what you see here, the increase from 0.5 to 1 milligram per liter orthophosphate was actually implemented in the Halifax and Dartmouth water systems. And we've been involved in monitoring to determine the effect of that increase in corrosion inhibitor on lead release at sites within the two water systems where lead service lines, full or partial, are present. So before I get into those data, I do want to mention seasonality and the importance of seasonality in monitoring lead release. So the available data that we have within the Halifax water system show that lead release specifically from lead service lines and from the entire plumbing network over short stagnation periods is correlated with water temperature. That relationship is probably fairly complex and involves the solubility of individual lead minerals, which may or may not be temperature dependent. There are a lot of other factors that we need to consider, other seasonally varying water quality parameters. Natural organic matter is an important one. In the Halifax system, aluminum coagulant residual is a potential consideration that may be quite important. But I've shown the correlation between water temperature and total lead release for two sites in Halifax, where 13-liter sample profiles were collected following a short stagnation time and the apparent temperature dependence. So for first draw samples, especially after a long stagnation period, this is not necessarily true. So there may be no temperature dependence, and there may be other seasonal factors that are more important, such as aluminum coagulant residual or natural organic matter. So with that in mind, we have a proper comparison from the 0.5 milligram per liter phosphate dose to the 1 milligram per liter phosphate dose. And by proper comparison, I mean in this case that we've accounted for seasonal variation. So at this single site, we collected 13 by 1 liter sample profiles in summer 2015 on 3 occasions. And we collected 13 by 1 liter sample profiles again in 2016 at the 1 milligram per liter phosphate dose. So again, you can see an apparent temperature dependence in lead release, but a substantially lower overall lead release, and this is total lead released over the 13-liter sample profile in each case. So at this single site, we see an 18% reduction in lead release, 2016 relative to 2015. We have incomplete comparisons for 10 other residential sites with full or partial lead service lines. In this case, we're talking about 7-liter sample profiles. And I've shown them here. Again, each point represents total lead released over that 7-liter sample profile at a phosphate dose of 0.5 milligrams per liter in April 2016. And that's compared in blue with a follow-up sampling round in June 2016 at an orthophosphate dose of 1 milligram per liter. And again in August, an April to August comparison. So as we saw previously, points below the y=x line indicate that total lead released to those sample profiles is lower at the 0.5 milligram per liter dose compared to the 1 milligram per liter dose overall. Between April and June or April and August, we see an increase in water temperature. All other things being equal, we might expect to see an increase in lead levels, although we also see a significant reduction in the aluminum coagulant residual present in these samples, which is another factor that could be important. So we really need to, in order to fully do this analysis and make a proper comparison, we really need an April to April comparison. So we'll have to wait for an update on these preliminary data, but encouraging results thus far, showing a decrease in lead release or an apparent decrease owing to the increase in phosphates. So I'll end with just a couple of summary thoughts. First, data from our Halifax lead service line replacement study did show that partial lead service line replacement was not a reliable strategy for reducing lead release. Second, corroded iron distribution mains play an important role in lead release to drinking water. And the most important implication, I think, of that finding is that removing iron or preventing iron release could have significant benefits for lead exposure. And finally, our preliminary data show that there have been promising results following a relatively small increase in the dose of phosphate within the Halifax and Dartmouth water systems. We'll have to wait for further confirmation of this due to the effect of seasonality, which complicates the analysis. So I'll acknowledge, of course, my PhD supervisor, Dr. Graham Gagnon, Wendy Krkosek, and the team at Halifax Water, and both staff and students at the Center for Water Resources Studies. Thank you very much.
Does anyone have any questions?
Probably said why, but why do you expect that when the lead lines were replaced, that the lead levels went up? Was it disturbance of the other parts of the system? Or?
You're talking about a partial replacement?
Yes, partial.
So there are both physical disturbances associated with replacement, pipe cutting, but there are also electrochemical interactions between copper and lead that can accelerate lead corrosion.
Okay.
So those are the two main concerns.
Okay, good. Thank
Yeah.
you.
Yeah.
So your all the Halifax sampling done, I guess, with Halifax water, not really with water from Halifax.
Water,
So
yeah.
it's generally stagnant, or that's not stagnant, but the conditions don't move much through the year. So if you were to take into account moving outside of Halifax, anywhere in the Maritimes or in the U.S., and you vary parameters like pH, alkalinity, chlorine residual. I mean, you mentioned natural antimatter and aluminum residual, but what would you suggest is an optimal water quality set of parameters to manage lead corrosion?
Another question.
And I don't think there's one optimal set of parameters. It really depends on the system. There are a number of different strategies. Some water managers go for a high pH type of strategy. Some go for promoting the formation of very insoluble lead solids within lead service lines, such as lead dioxide, by maintaining a high chlorine residual. Others use orthophosphate.
So would you suggest there's any science behind trying to derive a higher mineral balance to control lead, or would that just be a focused approach?
Mineral, you mean
Alkalinity. Would you,
like increasing alkalinity?
I mean, I've read through that in the health canvas stuff, and I don't remember what it says, and it's conflicted with what it's anyway, but
Yeah.
to hardness and alkalinity, all of the things being constant, have an impact on lead corrosion.
Oh, sure, they have an impact. I wouldn't rely on increasing alkalinity to control lead release. I think I would be fairly in line with most other experts, or most experts,
So
on that.
higher pH in conjunction with corrosion inhibitor. Like,
Well, that's a little bit complicated too. It's really specific to there really is no one size fits all, because orthophosphate has an operating range. I mean, orthophosphate minerals, simple ones, have a solubility minimum in the circumneutral, or in the slightly basic sort of 7.2 to 7.9, kind of 7.8 kind of range.
Yeah.
But yeah, increasing pH is pursued by some as certainly as a strategy.
No, there's a point of getting at is there's a whole block of people that the deal with that are just want to start add an inhibitor at pH 6.3 water. They don't need to correct what they anyway.
Oh, right. Yeah, of course. I mean, yeah, inhibitor addition has to be done in conjunction with pH control.
Isn't part of the problem if you're dealing with traces, real traces here? If you're trying to control the solubility, you're trying to control the solubility at trace levels.
Right.
I get more involved in mining at their order of magnitude larger. It's not hard to control it by doing this and that.
Right.
But I would say part of the problem here is that you're dealing with, one is dealing with real traces. And,
Absolutely.
Yeah, that makes it all the more difficult to say, because that would have been my first reaction, was why don't they just make sure they got alkaline water? If you know, if I was just sitting here talking about it, and then I realize you're dealing with traces.
Yeah, right. So
and absorption being a very important. There's a whole bunch of factors there.
yeah,
That you can't just say we'll do one thing or whatever, and it'll take care of it.
exactly. You know, monitoring has to be an integral part of the solution. And lead carbonate minerals are actually fairly soluble.
Yeah, at these.
Yeah, they're insoluble,
lead
but
oxide, lead hydroxide, and so on. That's right. What we're talking about here, they're quite
yeah,
soluble.
in this context, they're fairly
You
soluble.
can't just use the solubility curves and go, we'll hit for this.
Right.
No.
Right.
No. Whereas in other industries where you're not trying to produce a drinking water, you know,
That might be
maybe
enough.
Thinking about it, you can take those approaches.
Yeah, exactly.
Great, thank you, Ben.
Okay, first of all, thank you, Amina and ACWWA, for organizing this Lunch and Learn series. It's a pleasure to be part of the first one and kind of setting the stage for future ones, and I'm glad that we were able to get the video feed to work this time around. And thanks to Ben for giving a great overview of some of the research that's been done at Dalhousie University that has really affected our practice and policy at Halifax Water. So my name is Wendy Krkosek. I'm the Water Quality Manager at Halifax Water. And today I'm going to talk a little bit more about how some of that research has impacted our policy and also what our current corrosion control strategy is and our lead program in general, and some thoughts on where we're going to be headed in the future. So a brief presentation overview. I'll start with a little bit of a background on Halifax Water and lead in our system, where we were historically and where we are today. Talk a little bit about understanding the impacts of particularly Ben's research, but other folks in the research group at Dalhousie as well. Then I'll talk a little bit about our current Halifax Water lead program, talk about some of the new initiatives we've put into place this year, and finish with our path forward. So in Halifax, we have two water systems. We have the J.D. Klein Water Supply Plant, which supplies Halifax, Bedford, and Sackville. And we have the Lake Major Water Supply Plant, which services Dartmouth, Coal Harbour, Eastern Passage. In total, we have 83,000 service connections. So that's kind of the current snapshot of our utility. Just to give sort of a bit of an overview, as Ben mentioned, water in the water mains in Halifax is virtually lead-free. We don't have lead water mains, so the lead that's coming is coming from either the lead service line or from lead solder in houses, which lead tin solder was banned in 1986, but we still see a lot of it. And also, historically, brass fixtures could have a significant portion of lead as well. So those are the three main sources, with the lead service line definitely providing the bulk of the lead issues. And a similar figure to what Ben had, just to remind you that there are two different portions of the service line. There's the public portion and the private portion. And when it comes to Halifax Water, we own the portion from the water main up to the property line or the curb stop. And then the portion of the water or the service line from the curb stop into the home is the homeowner's responsibility. So as a regulated utility, we're not allowed to spend rate-based funds on private property. So this becomes a little bit of a challenge in some of the slides I'll be presenting later on. So historically, Halifax Water had about 15,000 lead service lines. Prior to Halifax Water being an integrated utility, it was two separate utilities. There was the City of Dartmouth and the City of Halifax. And so in the 70s in Dartmouth, they pursued an aggressive lead service line replacement program based on infrastructure funding. And they were able to replace about I would say 90% of the public lead service lines, so there's an estimate of about 500 remaining on the public side in Dartmouth, but we don't really know how many are existing on the private side. In Halifax, the approach was a little bit different. It wasn't one massive program. It was more in conjunction with the City of Halifax street paving and renewal projects. So anytime there was street paving or sidewalk renewal, we would go in and replace all of the public lead service lines on that street. So in both of those situations, we're creating partial lead service lines, as Ben talked about, which is not really the greatest practice we now realize. Again, in Halifax, we don't really know how many private lead service lines there are. We're estimating there's about 2,000 public lead service lines in Halifax. So, but we estimate that the private portion is significantly higher than that. The map I have on this slide kind of shows, it's hard to see in this room, but it shows the area that we're really concerned with in Halifax and Dartmouth that could have lead service lines. And it's basically peninsular Halifax, anything contained within the circumferential highway in Dartmouth, and a small portion that kind of leads up to our historic water supply at Chain Lake. We have a corrosion control program in place, which I'll talk about in a few slides, and we've always been compliant with regulatory sampling requirements for corrosion control. So why do we need to change this approach? What are some of the issues? There's a current shift in the industry towards complete removal of lead service lines. So it's now generally recognized that without removing the lead service lines from the system, corrosion control is not really going to be able to manage all of the lead that's in the system. So there has to be a balance between corrosion control and full lead service line replacement. And at our current rate of replacement, which is about 25 public lead service lines per year, it's going to take us 100 years to replace the lead service lines just on the public portion. So we need to make some changes to our program. As I mentioned before, we're not really sure how many private lead service lines there are, but we estimate that there was less than 10% uptake at the time that we were doing the public portion for a variety of reasons, but mainly there wasn't a lot of public outreach historically. The issues with lead service lines weren't really known, so it wasn't really pushed as an issue. And then, as I also mentioned, coordination with the city pavement management system in Halifax has led to partial replacements in the past. We've stopped this practice, as I'll get to in a little bit, but that was sort of the way that we got rid of most of the public lead service lines in the past, so we need to find a new path forward. So now I'll briefly touch on some of the research that Ben described and how that's impacted some of our policy. So this is another figure that was taken from Ben's paper on full and partial lead service line replacement. And basically, again, just saying that full lead service line replacement does lead to decreased lead. However, partial lead service line after 6 months still has a significant number of homes have elevated lead concentrations compared to pre-replacement. So these samples, this program that we have takes samples prior to replacement, 72 hours post-replacement, 1 month, 3 months, and 6 months post-replacement. So what kind of impact has this had on Halifax water? In 2012, we stopped doing partial replacements wherever we could. There are still circumstances where we do them, which I'll get into when I talk about our current policy. And also the industry is moving towards this removal of all lead service lines, public and private. So it's something that we're starting to explore. How do we put policies into or practices into place that encourage homeowners to conduct their side of the service line replacement as well? Again, Ben's figure on the far right there shows a pilot scale research study that showed that there was a correlation between cast iron mains and lead release, and also that a doubling of our orthophosphate dose would have an overall decrease in lead release. So as Ben mentioned, we've done a few things on this front since that study's been done. So we implemented a doubling of the orthophosphate dose in April of 2016, and we're monitoring. We started with 40 homes. We're monitoring quite a few less now because a lot of them have actually undergone service line replacement once they found out their lead concentrations. But we're monitoring that for a year to see the impact of that orthophosphate dose. This research also gives us the ability to target certain areas of the distribution system for lead service line replacement on the public side. So we'll definitely be focusing on areas with cast iron mains. And then lastly, another thing this has kind of led to is we're going to be installing dedicated pipe racks within our distribution system so that we're going to be able to monitor changes to corrosion control strategies in the future. So right now we rely on customers doing the sampling for us, and that can be quite a challenge. So this will enable us to just go in any point in time, have any type of stagnation regime, and take samples whenever we want, so we can monitor the changes in our corrosion control program. To talk a little bit about sampling, so the current US EPA lead and copper rule and the Health Canada corrosion guidelines use a first liter, first draw sample post 6 hour stagnation for their compliance with corrosion control. So what we have found through Ben's research and the LSL replacement sampling program, and other people have found as well, is that this is not a good indication of peak lead, peak exposure to lead. So this figure shows 115 homes with partial or full lead service lines, and the blue bars represent the first liter lead concentration, and the red bars represent the maximum lead in a 4 liter profile. So as you can see, only 28% of the samples actually had peak lead in that first liter. So this isn't really a good way to sample to understand lead exposure. So the impact of this research was that in 2014, we changed our practice from doing just first liter post-stagnation to profile sampling for any customer that has lead or suspected lead on the premises. So our Health Canada program now, we don't just do the first liter, we do a 4 liter profile plus a flush sample. So before I get into what our current lead program looks like, I just want to talk a little bit about sampling and what different type of sampling programs mean. I think both Ben and I could probably talk about an hour or two about this topic, but just to give you a bit of an indication of how complex this can be. As I mentioned, for compliance sampling, in both the US and Canada right now, it's based on that first liter sample, which is not necessarily indicative of lead exposure from the lead service line. So if we are looking for samples that would indicate lead exposure, there's a variety of different ways that this can be done. The general consensus is some sort of a profile sampling rather than a first liter or a flushed sample, because that gives you that sort of maximum exposure. There are different jurisdictions have different ways of doing this. We use a 6 hour stagnation. Ontario, I believe, uses a 30-minute stagnation. There's also some jurisdictions that use a random daytime sample, but with a combined profile sample as well. So each one of those situations will give you a different lead exposure. Obviously, having a longer stagnation period will probably give you a higher lead concentration. There's also discussion around how to actually physically take the sample. What type of bottle should be used? The current thought is having a wide mouth bottle and allowing the maximum flow rate will give you a maximum exposure. There's also discussions around whether the aerator should be removed from the tap when you're taking the sample or not. And then Ben talked a lot about particulate versus dissolved versus colloidal lead and understanding those differences and understanding what it is that you're actually measuring, because they all have a different sort of exposure profile. If we want to talk about actually identifying the service line material, so a lot of times utilities will have records that are incomplete. So if you wanted to actually figure out non-invasively what the service line material is like, you could do some sort of a profile sampling in combination with a premise plumbing audit. So going into the home, actually understanding how long the lines are within the house, where the fixtures are, how long the service line is, both private and public portion, and then calculating the volumes of that, and then doing profile sampling and looking at the lead concentrations in those profiles will give you a pretty good indication of whether there is a lead service line or lead components within the system. It's not perfect, but it does help. So the figure on the far right here shows 3 different profiles taken from Halifax. So the top one is a full copper service line, and as you can see, lead levels are pretty low in first, second, third, and fourth and flushed samples, but there is a little bit of lead in that first liter that could be indicative of the lead in the fixture. The second and third profiles are just different examples of a full lead service line within Halifax. So in the first one, there's also probably some lead in the fixture combined with the lead service line, which is showing up in liter 4. And the bottom profile shows liter 3 and 4 as the higher concentrations. And as Ben showed, this can sometimes go up to 13 liters. So you really need to understand the length of the premise plumbing and the surface line. The last type of sampling would be evaluation of the corrosion control program itself. So this can be done in a variety of different ways. Distribution system sampling for general corrosivity of the water. Repeated customer sampling, so just going to a customer's home once doesn't really give you good indication. It has to be done repeatedly in order to understand the impact of your corrosion control program. And then pilot and bench scale testing is a really good way to be able to evaluate sort of initially the benefits of your corrosion control program. So with that said, I'll talk a little bit about what we actually do. So we do have corrosion control treatment. We do have corrosion control monitoring. We do customer sampling. We have our lead service line replacement program. We have exposure reduction initiatives and post-disruption or construction, which I'll talk about. And then finally, I'll talk about our public outreach and education initiatives. So brief history of our corrosion control treatment in Halifax. Prior to 2002, we had pH adjustment with lime. Then in 2002, we introduced a zinc ortho polyphosphate blend. And we used different combinations of that up until 2015, where we removed the polyphosphate component because it's been shown that polyphosphates can actually lead to an increase in lead release. And then in 2016, we doubled our dose of orthophosphate to 1 milligram per liter as PO4, which is where we're currently operating. What do we do for corrosion control monitoring? So in the distribution system, we take samples biweekly at 21 different sites in Halifax and Dartmouth. We look at our orthophosphate residual, aluminum, manganese, iron, zinc, chloride, sulfate. Obviously, we can't look at lead because lead is not in our distribution mains, but this gives us a general idea of the water quality in our system. We also do quarterly monitoring of metal coupons at 10 different sites. So this is a measure of the corrosivity of the water again. It's not necessarily a measure of a tendency for metal release because these are new coupons that we're putting into the system every quarter. As I've talked about previously, we do a variety of bench and pilot scale research in conjunction with Dalhousie University, and we also hire consultants to do things like analyze the scales inside our pipes and provide recommendations on our overall corrosion control treatment strategy. And then lastly, as I mentioned before, we're instituting a program where we're going to have dedicated lead pipe racks in our distribution system, which we're really excited about. So in terms of customer corrosion sampling, we have a variety of different ways that we get into customers' homes. So first of all, we followed the Health Canada corrosion program since 2011. And as I mentioned before, we changed our sampling strategy so that we now do tier 2 sampling for all homes that have lead or suspected lead on premise. So we target 100 homes. We target 50 with lead service lines, which can be a challenge every year to find participants. And usually often once people participate in the program and they have a lead service line and they find out their results, they do undergo lead service line replacement, which is great, but it means we need to recruit volunteers every year into that program. And it also means that we don't have consistency in the homes that we do sample. So as I mentioned before, when you're looking at your corrosion control treatment effectiveness of that treatment, you can't really use this data for that purpose because the homes are always changing. Results of our first liter post-stagnation have always had a 90th percentile less than 15 micrograms per liter, which is the action level. However, we do definitely have samples that are above that value, especially if we look at the second, third, and fourth liter samples. As part of this program, we provide results letters to customers, and we explain what the results mean, and we provide instructions on minimizing exposure if their levels are above guideline levels. We also have customer-initiated sampling. So anytime we have a customer inquiry about lead, we offer complimentary sampling. If it's thought that they have an unknown service line material or they have a lead service line. So we use the same protocol. We do a 4-liter profile sample and a flush sample. And again, we provide letters with results similar to our annual program. And we've had a significant increase this year in the number of customers that have called to request sampling. And We think this is largely in response to the Flint crisis late last year. So people now have an understanding of what lead means and how it can actually impact their families. And so we've definitely seen an increase in customer requests. Our lead service line replacement program, this is what the research that Ben was talking about. So we offer it to any customer that's undergoing a full or a partial replacement. We've had 200 customers since 2011. Again, it's the same protocol as the annual residential monitoring, so a 4-liter profile plus a flush sample. And the sample analysis is conducted by Ben and his team at Dalhousie. In terms of our actual lead service line replacement program, as I mentioned in 2012, we implemented a policy of not doing partials unless absolutely necessary. So the only times we do service line replacements now is following a private replacement. So if the homeowner decides to do their portion, we'll come in afterwards and do our portion. And then we do, there are certain situations where we have to do partial replacements, and that's if there's any sort of an emergency situation or a leak on the public portion, we will then replace the public portion because we're already going in and creating a disturbance. And likewise, if we have a water main renewal project ongoing on a street with lead service lines, we will perform partial replacements, and again, that's because we've already disrupted the service line by doing the construction. But we make every effort we can to educate the homeowner on the benefits of doing the private side as well. A new initiative we've implemented this year is closing the gap on that timeline between public and private renewals. So one thing we're finding is when the homeowner would want to do their portion of the service line, it would then take us a couple of weeks to come in and do our portion, so they're left with that partial service line replacement for a few weeks and increased lead exposure, and then we disrupt everything again and they have that second exposure. So and we can't really minimize that because we can't do our portion until we find out that they've completed their portion. We have to inspect it, we have to get locates done, so it's a minimum of a 1 to 2 week period that before we can get there and then organize our crews to get out there. So we now have a standing offer with 3 different contractors where we have a contract with the contractor and then they develop their own contract with the homeowner and they'll do the whole job as one. So they'll do public and private as one job. Customers can still hire their own contractor if they want. They can go either method, but if they do that, they will have a partial replacement for a short time. And we've had 10 customers use this program since July. So in terms of exposure reduction initiatives, so we provide flushing instructions. The pamphlet that's shown on this slide is an example of what we would leave as a door hanger. So anytime somebody's doing work in the area that may disrupt a service line, or anytime we do a service line replacement, we leave this with the homeowner. And it describes what to do flushing-wise for up to 6 months post-disturbance. Another initiative we've implemented this year is point-of-use filtration units that we provide post-disturbance or construction. So in conjunction with Dalhousie, we tested several point-of-use pitcher-style filters for lead removal, and we chose the best one, and we now supply 1 filter and replacement cartridges anytime there's a lead service line replacement or anytime somebody takes out a permit to do a lead service line replacement. So that's actually just started within the past couple of weeks. In terms of public outreach, there's a lot of different ways that we do this. So as I mentioned, we provide results letters to customers following any type of sampling. We do talk to the customer pre and post construction or replacement and give them information on flushing instructions. We have significant outreach when we're doing water main renewals to try to get uptake on the private side. We have a website that we're continually updating, and we're hoping to get the map that I have on this page that shows sort of the hotspot areas of lead up on the website so that we can start to create a bit of a discussion. And it doesn't show where the lead services are, but where there are areas there could be lead services. So we hope that it'll encourage customers to give us a call and have a conversation. We're reaching out also to regional organizations, so the Nova Scotia Association of Realtors, building inspectors, plumbing associations, because those are often the folks that find the lead service lines, and we feel as though at a point of sale is a great opportunity to actually replace the service line on both public and private portion. We've also published in AWWA Upflow magazine, peer-reviewed journal publications in conjunction with Dalhousie, and we provide information in bill stuffers and our stewardship report and water talk as frequently as we can. So new lead initiatives for this year. I've talked a lot about this already, but just in summary, this year we've had an increase in our lead service lines that have been replaced, so we're double our normal number, and there's two reasons we think for this. First of all is we've had that increase in customer-initiated requests due to the Flint crisis in general, and a lot of those folks have undergone lead service line replacement. And also this bi-monthly monitoring program that we instituted this year, a lot of the, I think we've had 10 of the residents have now undergone lead service line replacements as part of that program. So our corrosion control, sampling, and monitoring, so we've instituted that bi-monthly monitoring program. We're putting dedicated lead pipe racks into the system. We've had that increase in customer sampling. We're closing the gap on the time between private and public portions of lead service line replacement. We've initiated a program for handing out filters post-disturbance or renewal. And we're also working on creating an inventory, so trying to really figure out where the lead service lines are. So we've developed this map as a first step of homes constructed prior to 1960 as an indication of where lead may be within the system. And we're also starting a program to replace all of the meters within our systems, which means we're going to have staff in every one of the 83,000 homes. So it's a great opportunity to collect information into our database, at least on the pipes coming through the walls or through the floors. So our path forward, what does it look like? Really our focus, the focus in the industry is towards removal of lead service lines. In December and January of last year, the National Drinking Water Advisory Council in the United States provided recommendations to the EPA on modifications to the lead and copper rule. And basically these 5 bullets are what's contained within those recommendations. And really it's a shift towards replacing all lead service lines, public and private, which is going to be a big challenge for utilities. As I mentioned before, we can't spend rate-based funds on private property. So developing initiatives where we can encourage homeowners to conduct private replacement is going to be a significant part of the challenge. And communicating with customers is going to be, we're going to have to really increase that part of the program. Working on developing an accurate inventory so that you know that you've actually replaced all of the lead in the system. But while all of that is happening, there's still a need to provide corrosion control, and there always will be. There will be those small sources of lead in the fixtures and in the lead tin solder that need to be managed. And then lastly, there's the continued sampling and monitoring components. So continuing with the customer-initiated sampling and compliance monitoring. And so with that, a few summary thoughts. So Halifax Water's corrosion control or lead program is an evolving process based on research and best practices. Moving forward, we're going to be looking towards replacing lead service lines, both public and private, and then controlling the other sources of lead through optimized corrosion control treatment. So that means a continued partnership with Dalhousie University to further our knowledge base and understand lead within our own system and how to best minimize lead exposure. And with that, I'll take any questions. Yes?
For those who might have a concern,
Yes.
such as my daughter in downtown Halifax over at home, what's the best way to sort of get involved? Is to go onto your website initially, or to give something?
You can email lead@halifaxwater.ca.
What is it again?
lead@halifaxwater.ca.
Lead@Halifax. Sorry to take time.
No worries.
Water.ca. That's okay. Okay, it could be better.
Yeah.
So
Or we have information on our website, ways to contact us there.
Get used to it.
You can call our customer service line, and those requests will get forwarded to us as well.
Thank you.
So, no problem. Spread the word.
Well, it's important.
Yeah,
I've read
definitely.
all the Flint stuff, a lot of it. You realize, it's good that you folks are being open and saying this is where we're at and this is what we need to do. That's good. Just keep doing that.
Any other questions?
I'll just offer up that I was in New Jersey last week for AWWA section meetings. So this is where all the AWWA sections from Chesapeake, agenda for the meeting to talk about ACWWA stuff. But being like apparently everything in ACWWA right now just got railroaded into lead for half the time, where the different sections and the people that were there from the sections just one by one just got up and made their own rant about how big of a problem it is for them now. New Jersey has a governor order to sample 10,000 schools by the end of November.
Wow.
Under LCR protocol. So they haven't figured out who even is going to do the sampling, letting alone the protocol. They don't know if it's going to be the school board or the public utility, but the amount of the groundswell of fear among utility employees in the U.S. is really considerable.
Yeah.
So then Jamie got up and basically said, like, we something akin to like, we produce all the data you guys need, so just give me a call. We can help you out, even though they couldn't identify us on the map.
Well, we've had requests from the EPA for the data sets produced from the LSL sampling program, because it is really one of the biggest data sets that exists, because most utilities don't do profile sampling to that extent, and especially repeatedly in homes. So it is a really great data set. But yeah, it's definitely a huge conversation in the US. It's starting to be a little bit more in Canada, but we really weren't as affected by Flint as folks in the US. So it made a little bit of media attention here, but not significantly. Anything else?
No more questions? Thank you so much, Wendy and Ben, for So I hope everyone enjoyed the presentation. If you have comments on your presentations, that would be great for our next lunch and learn, or people that you think would be good